the third speaker is Professor MKU of Academia Sinica. He will tell us about the recent advancement in beta ion selenide and related superconductors. Please.
Well, okay, first I'd like to show this picture. This is where I'm now, in the east coast of Taiwan. So when your time, please come. And this is up and down, right? Let's see. Okay. Well, let me use this. Okay, so what I'm going to tell you in this, the next 30 minutes is what we have learned recently about this iron selenide related superconductor. I think first I'd like to acknowledge my collaborator. Actually, one of the very important person, Dr. Wang, he's in the audience. And we have many people who are working in material and also some interesting characterization using either TM or a femtosecond pound probe experiment and so on. Okay, here's the outline. First, I'd like to stress a little bit about this issue that has been discussed for quite a while. In fact, yesterday we heard a very nice talk from Xinjiang about how you anneal the sample and you can evolve and see the difference in the electronic structure. So there's the issue of this stoichiometry and the real phase diagram for this iron selenide. And I briefly mention about some of the observation, and I'll talk about some of the recent work by observation of the gap opening at low temperature and the implication summary. All right, this is generally the phase diagram for all the iron-based superconductor. However, for particularly the iron cationic, iron selenide or telluride, from the early days, people mostly cited that the iron telluride is the parent compound. And then you dope with the selenide and becomes superconductor. Iron selenide, which is magnetic and non-superconducting. Okay, that people have been using that. And we were going to show you that probably we have to think it differently based on some of the recent work. In order to address it, in fact, in the beginning, the iron selenide, whether it's 1-to-1 or iron rich or iron deficient, has been an issue all the time. Okay, and in order to do this, well, we have to be really careful. But here, of course, there's a very interesting result, I think mentioned by Xinjiang and Maw-Kuen also. That is the observation of very high TC of iron selenide under high pressure. Okay, and here is a very complete work by a Russian group in collaboration with Carbon in Princeton, showing a very intensive changing of transition temperature with the pressure. Okay, which means that there is indeed some kind of interesting phase diagram in this particular system, and how, now you can use the pressure, but how can we do it and look at that chemically, okay? And with this high TC, what is really the origin? So we decided that might be some interesting small interface effect, especially the recent observation of a very high TC by Xinjiang and also Maw-Kuen using the one unit cell and selenide. So we decided that we probably should really look at the material from the nano-dimensional size, okay? So we recently, before I do that, of course, there are a lot of interesting features in terms of electrical resistivity in this particular selenide, which I'll come back in more detail, okay? But if we look at in more detail this, by analyzing the data here, by taking the differential immediately you see some very interesting feature. Okay. One, of course, this is the superconducting transition. Then there is a one kink, small kink around 100 or 90 Kelvin. Okay, and we clearly associate that with some kind of structural transformation. I'll come back to that. In fact, there's one interesting anomaly around 40 K. Whether this is something to relate to that high pressure phase. Okay, that's interesting. So we decided to use a different approach by making a nanoparticle. And because the nano technology now, there are many ways you can synthesize. And this is a very simple method. We can make a very pure, clear particle. Well, indeed, with certain composition and proper time annealing, you really see the clear 40K transition magnetically, but it's difficult to transport. Okay, so we further look at, this is another particle, but with that slightly different composition. This is tellurium with sulfur. I'm not going to address that, but this is interesting. You really see something around 30 Kelvin, a clear magnetic transition. Okay. So we are able, we develop another technique to grow very high quality nanowire in the dimension of 100 or tenths of a nanometer. And the lattice parameter is always found to be a little bit smaller than the bulk. Okay. And then we were able to make the contact and do the measurement. And that's what we saw in several of these iron selenide nanowire. Okay, here, this is the iron selenide. Unfortunately, so far, we have not been able to really see the resistive transition in this iron selenide nanowire, which are actually probably important for us to understand what's going on here. But for the selenide with the tellurium doping or this tellurium sulfide, here there's the interesting feature I want to mention. This is the high temperature, this bond, broad shape of that. Well, but we analyzed in more detail the composition, and we found that actually all the sample has this kind of ratio. It's actually the iron, the selenium to iron ratio is about 1.26, which is iron deficient in most of just the high quality crystal. Okay? And this is close to the so-called 4-to-5 ratio. Well, remember this is a double layer. You have 2,4,5 compound, which gives you a 40 Kelvin. Okay, so that means this iron deficiency could be really the important thing in this whole series problem. And in fact, later on, we decide to examine more carefully on some of the crystal we grow using high pressure technique, which are very high quality and give a very good electrical or magnetic transition. And we found indeed there is a very interesting extra peak in this TEM image, and showing that there's some kind of superstructure that is indicating some kind of iron vacancy. And one of my associates really make a clear simulation of the system and decide that there is a 2x2 iron vacancy order. And this one actually is not superconducting for this particular one. Okay. And the composition-wise, from this system, it clearly shows that it's 3.4, 3 to 4. Iron to selenium ratio is 3 to 4. So in fact, we do have this tetragonal phase, 3 to 4. Usually, the iron selenide in the phase diagram, the material sign, phase diagram, you only show the hexagonal phase, the 3 to 4. But now, under certain conditions, you can stabilize this tetragonal 3 to 4 phase, which is non-superconducting and with some magnetic feature. We are doing this in more detail now, because now we can do other way by, for example, from 2,4,5, then extract the potassium out to make it a pure iron selenide, and so on. Okay, so that's all this result. All indicate this iron actually is deficient. Okay, So we are now proposing this kind of a new phase diagram, which need to be studied in more detail, okay? That we probably have a parent compound close to this kind of a tetragonal 3-4, which is magnetic, non-superconducting. And then after doping, then you gradually move into another. You have many interesting 4 to 5, 7, 8 or so. And then the 8-degree Kelvin 1 to 1 is probably the overdope region. Okay, so this is consolidate or more uniformly compared with the other phase diagram, the arsenide or the cupra. Okay, so this is our proposal for the phase diagram, and that's something that probably will be much clearer if we can study more. And I think we're not able to, I've been asking people to really do some initial calculation to see the band structure and whether that will be consistent with what Xinjiang was mentioned. If you annealing with different conditions, how that evolved from one phase to the other. Okay. So this is the tentative phase diagram we propose based on this recent study using different kind of material in more detail. All right, and I want to move to the second part. First, let me show you what kind of feature we see in this iron selenide. In fact, many of the features I mentioned here also appear in the other necktie, iron arsenide 122 or 1111 system and so on. Okay. The first one, of course, typically this resistivity, as I mentioned already, there are several features. One is a very high temperature, bro. It's called a kind of bomb here. And there's a small dip, and of course, superconductor transition. And as mentioned, there is some feature around 40 Kelvin, okay? Not shown clearly here. But if you use a differential, you can really see that. Okay? And what are those features? Let me first talk about this 90 Kelvin, something around 90 Kelvin, which was identified the first time we discovered this material. By the way, I want to mention that not only this kind of a Bohr bond, but also for all the nanowire that show superconducting, indeed show this kind of interesting behavior. Okay? And this is the structure information we have in the iron selenide that shows superconducting transition. You see that there's a small distortion. Actually, it's really not that big. It's just its gamma angle that tilt from 90 degree to 90.3. So essentially, below 90K, you convert this from tetragonal to some kind of orthorhombic phase. Okay? But interestingly, this is the work by Carba's group, but we also have another by using chemical doping, but using thin film, different kind of technique. It clearly demonstrates that this low temperature distortion is essential for superconductivity. Okay? If you don't see, this is the result from Carba, by using different composition, they see that for a superconducting one, then there is a distortion for non-superconducting material, which has a higher, in their composition is 103, 1.03 or something like that, the iron reach that is non-superconducting. And it shows that the distortion disappears. So the conclusion is this: the low temperature distortion has correctly no distortion, no superconductivity. Okay. Now let's look at the other feature. For example, there's a thermoelectric effect. When you cool down, first you see one signal here around 220K, the crossover from the P to N. Okay, and more interesting is that when you go cool down to low temperature, there's a local maximum around 100 Kelvin, which is the distortion temperature that appears. So there is some kind of electronic variation we associate with this structure distortion. Okay? And not only that, you can demonstrate, this is actually by Thomas they are using copper doping to suppress superconductivity and when it's non-superconducting, you see there's no such feature. This local maximum disappear, gradually change. And for non-superconducting one, then you will see that anymore. And this is for another comparison of this 1-2-2 system. And it's really clear by Teng Xianhui's group that in this two non-superconducting region, you don't see any feature, but only those composition that shows clear superconducting transition, you have this local maximum, okay? And the value, of course, become much smaller. And for Hall effect, that also similar. There is a feature that indicating some kind of electronic structure change around 140 or 50 Kelvin. Okay, and this is from all this superconducting one. For non-superconducting one, that you don't see that kind of behavior. Okay. More interesting, this is something we don't quite really understand, is that we were using this iron selenide single crystal. Now, it's interesting that the crystal usually it has a growth habit along this the surface of 101 instead of normally 001. Okay, which means that along this iron selenide line. And if we look at this field along this 101 and perpendicular to 101, which means that one is along this say 101 plane and then perpendicular. If we brought it up, you see this. A strong anisotropy between these two directions. And that separation is appear around 100, the one close to where there's a broad bond appear in the resistivity, as I showed you earlier, and also has something related with the Hall effect, maybe closely. So there's a strong anisotropy along this 101 plane and then perpendicular to 101. Means that this iron selenide seems to be more like it's electron movable. If you look at the behavior, and this is more like localized along this stuff, perpendicular. And that make you think this has something to do with the orbital effect. Right. Okay. So that's, well, okay, we already know that there's a strong spin fluctuation associated with this superconducting one. I think the most beautiful data from Imai's group, and they were using even study under pressure and found that the pressure actually enhanced the spin fluctuation, and the TC is associated with the TC enhancement. Okay, so spin fluctuation definitely associated with the superconductivity, and as I mentioned, that also related to structural transformation. Okay, so let me give a quick summary. Okay, of what we saw. For all this experimental data show that the electric resistivity was first show a broad bond hump as about 200K, then slight dip at 100K. And I mentioned this 100K is clearly identified associated with the structural distortion. And of course, there's a 40K I mentioned earlier. And the magnetic susceptibility as 200K also exhibits an anomalous anisotropy between field along 101 and perpendicular to 101. Okay? And we think that has something to do with the orbital effect. And an anomaly in Hall coefficient at this temperature, changing density of state near the Fermi level. And number 4 is about this thermoelectric power measured by and show that the structural distortion occurred that appeared as a thermal power anomaly. And I didn't mention too much, but this chemical substitution suggests that there's very strongly suppressed this distortion on this. And several detailed local probe experiments, like I show you the NMR, suggest there's a strong spin fluctuation associated with the structural distortion. Okay, so later we decided that maybe we can use this optical measurement to study in more detail what how this observation can be, how can we link together with some kind of feature here. So we are using this femtosecond pump probe, and we're using the probe energy. Interesting, because this is basically this D to selenium P hybridization orbital. Okay, so we immediately saw that there is a transfer of optical spectral wave, and that appear around 140 Kelvin. Okay, remember the temperature I just mentioned, and this indicates its onset of some kind of orbital modification, right? And then we look at the low temperature signal of this in order to find out this carrier dynamic. And we see that when we cool down the whole spectrum, then change drastically at very short time domain. And this can be easily described by such a simple formula. And by analyzing the data for the phase relaxation, then this show that there is a very sharp rise in this coefficient. Okay, and this really strong suggests there's some kind of gap opening here. The absorption here. So this is the temperature where the 100, the spectral wave change associated with it. And actually, this is slow dynamic, which is the describing this kind of thermal carrier phonon thermalization. And we can use a simple model, and that also consistently showing there is a gap. Okay, I'm sorry. Okay, but the gap value, of course, is not much smaller, but by indicating it cannot be used in a simple manner, we should have a gap to describe this feature here. So the phase dynamic and the slow dynamic, they both indicate there's a size of, there's a gap open around 140 Kelvin. Okay? And the detail value, of course, need to be examined again. So evidence for the existence of a gap. And that gap clearly is associated with this distinct the correlation with this orbital modification. Okay, so this is sort of, and that also clearly can be associated with the thermal, the whole effect I just showed you earlier. Okay. All right, and those are really that tell us that might be some kind of pseudo gap and associated with this pneumatic order. Well, then the question is, what is the low temperature distortion can give us from this optical measurement? And we can study this using sub-nanosecond coherent acoustic phonon dynamic. This is a simple experiment, and just tell you the result. And if we did see that around 90 Kelvin, there's a stiffness. Okay, this is associated with structural transformation from this optical measurement. Okay, and actually this is very clearly showing that the onset really coming out from this kind of modification, and then end up with this structural distortion. So there's a close correlation between these two. Okay, here just for comparison, because 122 people has observed this kind of a transformation using the similar technique. Okay. So let me summarize that when we cool down, of course, there's a 200 higher temperature, they start to see some kind of fluctuation maybe. At the 140, 130 Kelvin, then you see the change of shear thickness, reduction of optical absorption, and others, suggest that the density of state change or the schematic phase comes in. And we also see this prolongation of picosecond. This is the carrier phonon thermalization, and this quasi-particle relaxation. Okay, so that really suggests strongly there is a gap opening near the Fermi surface, and then the spin fluctuation and modification of this electronic band structure developed near the temperature structured phase transition. And that certainly lead to, finally, to superconductivity. And how this story can be told is actually we need a theory to come out with the picture. So let me summarize what I present today is that we are proposing a potential new phase diagram for the iron calcinide. Instead of using the iron telluride as the parent compound, we should really go back to iron selenide, but with a tetragonal, maybe 3 to 4, with the iron deficiency, with iron vacancy order is a certain phase. Okay, that's the parent compound we have. Okay, and we should be able to do more experiment by, for example, by using a narrow wire of different composition to look at this annealing effect. And all observed anomaly from transport, magnetic, and optical measurement possibly is associated with the orbital magnification and some gap opening. And of course, the fluctuation, I think the distortion and spin fluctuation, they are all really important for this system to become superconducting. Okay, so that's my story. But this is the picture I want to show you. I have a colleague who is really interesting. He took a camera, every 3 days he came to the same site, and look at the background and see the cloud. And actually, there's a mountain you don't see in the back. This is our campus. Welcome to Taiwan. But I think I want to use this because also show that the core is the same. So the superconductivity is the same. But it can be different, for different measurement, different perspective, but everything should be the same. Okay.
How old is the building? How old is the building?
About 20 years. Anyway, so thank you, and welcome to Tonghua.
So now, it's open for discussion. Questions? Yes.
Hello. Yes. I find out the thermal power, which shows a great peak, right? Negative,
yeah.
Right. The value is like 80 or something. It's close
About
to
about 90K, yeah.
Right. It's close to the quantum thermal power, right? 86 microvolts per Kelvin. I'm just curious how to understand such a large thermal power. Thanks. Is that something
Actually,
from phonon
that's not
drag?
that big. Yeah. Well, I mean, this is, we can only tell that there is a structural change there. So some kind of electronic structure change at that temperature. That's all we can tell. But why? We need to more. The theory needs to tell us the story. But this is the feature, though. If you look at all the iron necktie or all iron superconductor, for the superconducting state, you always see that. For non-superconducting one, that feature gone. So this is a very important signature.
The sign of the power.
Well, it depends on the, this is the electron dose.
Sign of the particle.
Yeah.
The related.
I mean, these Hall effect, of course, they appear at a bit different temperature, but yeah, related to that, right. So we need theory help for this.
No more questions.
Okay.
Thank you very much.
Okay, thank you.